Okay, in this lecture, we're going to continue our section 6.3 material on step functions. And here we're going to talk about how we can use step functions to represent periodic functions and talk about the Laplace transforms of periodic functions. So let's start with a definition. We would say that a function f is periodic of period capital T if f of t plus capital T is equal to f of t for all values of t in the domain of our function. And we're familiar already with some basic periodic functions. For instance, the sine and cosine functions are periodic with period 2 pi. And the tangent function is periodic with period 1 pi. So in order to define a periodic function, we know that it is sufficient to give its values over a single period. And then because it's periodic, those values given over one period are just repeated for all values in the domain of that function. Now, some other common periodic functions are described here. I've given a few common ones. The first one we'll discuss is called a square wave. So let's consider the function f of t, which is defined as 1 on the time interval from 0 to 1. So let's look at our graph here. Time 0 up to time 1, we have a constant value of 1. Then on the t interval from 1 to 2, the value of our function is a negative 1. So we jump down to negative 1. And then we specify that this function is periodic of period 2. So for these initial values given on the time interval from 0 to 2, we will repeat these values with period 2 moving forward in time. Another common one is what's called a sawtooth wave. So if we consider the function f of t, which is equal to t, for values of t from 0 to 1, well, geometrically, we have f of t as t, so we've got a line segment moving from 0, 0 to 1, 1. And then we specify that this is periodic with period 1. So those initial values on the time interval from 0 to 1, we will repeat with period 1 moving forward for values of t. And another common one is called a rectified sine wave. So suppose that we consider the function f of t, which is sine t, on the t interval from 0 to pi. So on 0 to pi, we know that our sine wave starts at 0, it increases to a value of 1 at pi over 2, and then decreases back to 0 at time pi. And then we specify that this function is periodic with period pi. So we repeat those values for all forward time with period pi. So these periodic functions I'll say they appear in some nice applications for differential equations and engineering. And so let's discuss how to define a Laplace transform of these types of functions. So before we see how to find the Laplace transform of a periodic function, let me introduce a little more notation. I'll mention first, it is useful to introduce a notation for what we would call the windowed version of a periodic function f of t. So let's introduce the following notation. F with the subscript of capital T of t is the function defined by f of t over its initial domain from time 0 up to capital T and 0 otherwise. So a windowed version, or this notation for a windowed version of a periodic function, is describing one definition of my function over one period. For instance, for the square wave, we would have the initial values on the interval from 0 to 2. For this sawtooth wave, we would have the initial values on the interval from 0 to 1. Or for the rectified sine wave, we would have the initial values from 0 to pi. And that is what we are denoting as this f with the subscript t of t. It's one window of this periodic function. And so let's think about the Laplace transform of this windowed version of a periodic function. So I could denote it as capital F sub t of s. And by definition, it is defined by the integral from 0 to infinity of e to the negative st times the function I'm taking the transform of. And because of the piecewise definition of this windowed version of our periodic function, well, the only interval where it has non-zero value is the interval from 0 to t, where our function is defined by f of t, and it's 0 for all other values. So let's take a look at the following theorem. This next theorem will tell us how to find the Laplace transform of a periodic function. So here's what it says. Let us suppose that we have a periodic function f with period capital T defined on some interval from 0 to infinity. Then the Laplace transform of that periodic function f is given by the ratio of the Laplace transform of the windowed version of our function divided by 1 minus e to the negative s times capital T, where the Laplace transform of that windowed version was given by the integral we saw above. So let's see if we can establish this result. Let's take a look at the proof of this result. So let me start by saying we can note that a periodic function, f of t, can be written as a sum of copies of its windowed version, translated t units in the positive direction. So my function f of t, well, I can think of taking its windowed version on the first part of its domain from time 0 to t, and then I could add the values of the windowed version shifted capital T units to the right times my unit step function at times t plus the windowed version of my periodic function, then shifted 2t units to the right times the step function at time 2t, and so on. So by summing these copies of that windowed version, translated t units or 2t units or 3t units to the right, we can generate the entire function f of t. And so by the linearity of the Laplace transform, if I want the Laplace transform of f of t, I would take the Laplace transform of the windowed version plus the Laplace transform of the windowed version times the step function plus the Laplace transform of the windowed version times u 2t, and so on. And so let's take a look at what we have here. The Laplace transform of f of t would be given by the Laplace transform of the windowed version, f sub capital T of t, and then plus, for this next term, let's see what we have. I have a unit step function at time capital T times the windowed version shifted capital T units to the right. So by theorem 6.3.1, or property 13 in our table of Laplace transforms, the transform of this function would be given by e to the negative s times capital T times the Laplace transform of the windowed version, which we denote as capital F sub t of s. And then, moving to the next term, well, I have the product of a unit step function at time 2 capital T times the windowed version of f shifted 2 capital T units to the right. So again, by theorem 6.3.1, my Laplace transform would be e to the negative 2st times the Laplace transform of the windowed version of our periodic function. And so the other terms have a similar form. So if I factor out this common factor of the Laplace transform of my windowed version of the periodic function, I'm left with 1 plus e to the negative st plus e to the negative 2st, and so on. And so what we have now is capital F sub t of s times a geometric series of some terms. We could write this as the sum from 0 to infinity of e to the negative st raised to the nth power. And we know how to find the sum of a geometric series. it would sum to a value of 1 over 1 minus e to the negative st, provided that the values of s are positive. So we're left with the ratio of the Laplace transform of my windowed version of the function over 1 minus e to the negative s times t, or explicitly the integral from 0 to t e to the negative st times f of t dt over 1 minus e to the negative s times capital T. And this is what we wanted to prove. So let's take a look at some examples of finding a Laplace transform of periodic functions using this new result. In this next example, we are asked to find the Laplace transform of the square wave function that we had considered earlier, which is defined as 1 on the interval from 0 to 1, negative 1 on the interval from 1 to 2, and then has period 2. So that these values over that initial interval from time 0 to 2 are repeated. So we know that the first thing we need to calculate is the Laplace transform of the windowed version of our function, which is defined as the integral from 0 to capital T. In this case, we had a function of period 2 of e to the negative st times the function f of t on that interval. And here, our function f of t is defined as either 1 or negative 1. So let's take a look at what we have. We could split our integral into the sum of two integrals, the first of which from 0 to 1, where the value of our function would be a positive 1. And then we would add the integral from 1 to 2 of e to the negative st times f of t, which has a value of negative 1 on that interval. So let's evaluate these expressions. We now have an antiderivative of negative 1 over s e to the negative st. For the first integral, we're evaluating from 0 to 1. And then I'm subtracting negative 1 over s e to the negative st, evaluated from 1 to 2. So for the first integral, we have negative 1 over s e to the negative 1s minus, substituting 0 in for t, we get a negative 1 over s. So subtracting that value becomes plus 1 over s. And then I am subtracting, substituting 2 in for t. I have negative 1 over s e to the negative 2s minus a negative 1 over s gives me plus 1 over s e to the negative s. Or combining like terms, I'm left with a total of 1 over s minus 2 over s e to the negative s plus e to the negative 2s over s. So for my Laplace transform of this function, which I'll denote as capital F of s, we take the expression that we just found, and I divide through by 1 minus e to the negative s times capital T. And since this function was periodic of period 2, we have e to the negative 2s. Now to simplify this expression, well, I don't like the compound fraction, that is a fraction within a fraction. So I can eliminate that by multiplying my numerator and denominator by a factor of s, leaving me with 1 minus 2e to the negative s plus e to the negative 2s over s times 1 minus e to the negative 2s. And this can be simplified further by factoring. My numerator can be factored as 1 minus e to the negative 1s squared. And we're dividing by s times 1 minus, 1 plus e to the negative s times 1 minus e to the negative s. And so I can cancel then one factor of 1 minus e to the negative s, from which I have 1 minus e to the negative s over s times 1 plus e to the negative s. Okay. So using this new result, we have found the Laplace transform of this periodic function, the square wave function. So let's look at another example of this. Next, we are asked to find the Laplace transform of the sawtooth wave function that we saw earlier. Again, this function is defined as t on the interval from 0 to 1. So our graph, we have this line segment from 0, 0 to 1, 1. And then it's defined to be periodic of period 1. So we repeat these values for all forward time. Now to find our Laplace transform, again, we will first find the Laplace transform of the windowed version of this function. That is our capital F sub t of s, which is defined as the integral from 0 to capital T, in this case period 1, of e to the negative st times my function f of t, which on that interval is defined as t. So to evaluate this antiderivative, I need to make use of integration by parts. So let me choose part of my integrand as u, and the rest of it as dv. So here I would choose u as t, in which case dv would be e to the negative st dt. So du is then 1 dt, and v is negative 1 over s e to the negative st. So we have then our integral from 0 to 1 of e to the negative st times t dt. is equal to uv, so negative t over s, e to the negative st, from 0 to 1, minus the integral of v du, which would give me a positive 1 over s, integral from 0 to 1 of e to the negative st dt. Or evaluating that second integral, I have negative t over s, e to the negative st, minus 1 over s squared, e to the negative st, evaluated from 0 to 1. So evaluating at t equals 1, I have a negative 1 over s, e to the negative s, minus 1 over s squared, e to the negative s. And then I subtract what I get by evaluating at t equals 0, which would give me a positive 1 over s squared. So using our new theorem for the Laplace transform of a periodic function, I would take what I just found for the Laplace transform of the windowed version, that is negative 1 over s e to the negative s, minus 1 over s squared e to the negative s, plus 1 over s squared, and divide by 1 minus e to the negative s times capital T. And for this function, we had period 1, so we're dividing by 1 minus e to the negative s. And for simplifying, again, I don't like the compound fraction. So to eliminate that here, I could multiply my numerator and denominator by s squared, leaving me with negative s e to the negative s minus 1 e to the negative s plus 1 over s squared times 1 minus e to the negative s. Or if we prefer, the numerator can be rewritten as 1, and then if I factor out a negative e to the negative s from the remaining terms, I'm left with an s plus 1 over s squared times 1 minus e to the negative s.